You ever watch a cartoon or a video game and just wonder, how do they do it? How does a character run and jump and flip all over the screen, but their shape stays absolutely perfect? Well, it's not magic, it's actually a secret code. And in this explainer, we're going to crack it wide open. We're talking about the hidden math that governs all movement, from our screens to the entire world around us.
So here's our game plan. First, we're going to discover the geometry that's hiding in plain sight. Then we'll meet the three master moves, the transformations. We'll see how coordinates bring these moves to life, unlock this super powerful idea of congruence, and then we'll connect it all back to the real world. Ready? Let's go.
All right, first things first. Let's totally redefine what geometry is. I want you to forget about dusty old textbooks for a minute. Instead, think of it as a dynamic set of rules. Yeah, that secret code I was talking about, that describes how things can move and change their position, all while keeping their exact shape and size. Okay, so let's circle back to that first big question. Think about your favorite animated character. When they're zipping across the screen, they stay perfectly, well, themselves, right? Their arms don't suddenly get longer, their head doesn't warp into some weird shape. So how do artists and programmers make sure that happens, frame after flawless frame?
Well, the answer lies in this really powerful concept called rigid transformations. And that word rigid is the absolute key. Think of something solid. It can move around, sure, but it's not going to bend or stretch or break. These are the mathematical rules that let an object change its location, but never ever its fundamental size or shape. So what are these so-called master moves? You might think there'd be a whole bunch of them, but what's amazing is there are only three. That's it. Just three foundational actions that describe pretty much every kind of movement you can possibly imagine: the slide, the flip, and the turn.
First up, we've got translation, which is really just a fancy way of saying a slide. Imagine you're moving a chess piece straight across the board. Every single point on that piece moves the exact same distance and in the exact same direction. No twisting, no turning, just a nice, smooth slide from one spot to the next.
And here's how the math tells that story. Let's just track one point on our original shape, what we call the pre-image. Point A is sitting at coordinates 0, 0. Now the rule for our slide is the vector 2, 1, which is just code for move 2 units to the right and 1 unit up. So for point A, you take its x value, 0, and you add 2. You take its y value, 0, and add 1. And boom, our new point, P, lands right at 2, 1. You do that for every single point, and you get a perfect, predictable slide.
Our second master move is reflection, the flip. And it is exactly what it sounds like. You take a shape and you flip it over a line, creating a perfect mirror image. I mean, think about a butterfly's wings, right? One is a perfect reflection of the other. That's symmetry, that's pure geometry right there in nature.
And just like sliding, there's a really simple code for flipping. If you want to reflect something across the horizontal x-axis, you just flip the sign of the y-coordinate. That's it. Want to reflect it over the vertical y-axis? You just flip the sign of the x-coordinate. It's such an elegant, simple rule. Okay, our third and final move is rotation, or simply the turn. A rotation spins a figure around a single fixed point, which we call the center of rotation. Think about the cars on a Ferris wheel turning around that center hub, or the hands of a clock spinning around the middle. The whole thing turns together as one solid piece. And you probably guessed it, there's a precise mathematical recipe for this too. To rotate a point 90 degrees clockwise around the center, the coordinates x, y suddenly become y, negative x. Now, it might look a little weird at first, but that's the exact instruction a computer uses to do a perfect turn in an instant. Every rotation has its own little coordinate swapping rule. Okay, so we've met our three main suspects: the slide, the flip, and the turn. Now it's time to put on our detective hats. Let's look at some evidence on the coordinate plane and see if we can figure out which transformation has been committed. All right, detective, here's our first case. Look at the clues. The original shape has a point A at 2, 3. The new shape, its image, has a corresponding point A' at 2, -3. Let's check another clue. Point B is at 4, 5, and it becomes B prime at 4, -5. Do you see the pattern here? The x value, it's not changing at all. But look really closely at what's happening to that y value.
Exactly. The y value is just flipping its sign from positive to negative. And if we go check our rulebook, we know the code x, y becomes x, -y means one thing and one thing only. It's a reflection across the x-axis. See? Once you know the code, the movement is totally obvious. Case closed.
So look, we've learned how to slide, flip, and turn shapes all over a grid. But what's the big deal? Why is this stuff so important? Well, the answer is a massive idea that's really at the heart of all geometry: congruence.
So what is congruence? Well, two figures are congruent if they are perfect clones of each other. We're talking same side lengths, same angles, the whole shebang. And the official mathematical way to prove they're congruent, it's by showing that you can get from one shape to the other using only our three master moves: translation, reflection, or rotation. If you can do that, they are certified congruent.
And honestly, this is the most important takeaway of this whole thing. Rigid transformations are special because they preserve everything that actually matters: the distances, the angles, the size, the shape. This means the original figure and the final figure are always congruent. It's a mathematical guarantee that they're perfect copies.
Let's put that idea to the test right now. Look at these two triangles. Are they congruent? Well, just looking at them, they kind of look like mirror images, don't they? And if we were to check the coordinates, we would confirm that triangle DEF is a perfect reflection of triangle ABC, right across the y-axis. And since we were able to map one perfectly onto the other with a single rigid transformation, well, we've just proven that they are congruent. It is that direct.
Okay, this is the part where it all clicks into place. We started this whole thing with a question about animation, and now we can see that these math rules aren't just for worksheets, they are the essential tools people use to literally design and build the world around us.
This quote from our source material really says it all, doesn't it? In computer graphics, every single time a character moves, the software is performing a rigid transformation. That is what guarantees the character looks right. Without these rules, animation would just be a distorted, glitchy mess.
And it's not just about looking good. In architecture, symmetry gives buildings their structural integrity. When one side of a bridge is a perfect reflection of the other, the architect knows for a fact that both sides are congruent. They have the exact same dimensions, the same weight distribution. That congruence creates balance and strength.
And what's really cool is you can combine these simple moves to create incredibly complex motions. Like, what if you want to rotate an object around a point that isn't the center? Well, it's just a simple three-step dance. You slide the whole thing so the pivot point is at the center, you do the simple rotation we already learned, and then you just slide it all back. Simple building blocks making complex results. So, from the pattern on a tile floor, to the spinning rims on a car, to your own reflection in a window, our world is just absolutely filled with translations, reflections, and rotations. You've now learned the secret mathematical code behind all of it. So the only question left is, where are you going to spot it next?